Okay. Getting back to this, there was the NO, so I'm curious if that has to do with endothelial cell damage. Excuse me, the NO. And there's multiple clinical trials right now if NO can treat and prevent COVID-19. NOs, remember the reaction of nitrogen with oxygen in air. So nitrogen is very hard to combust, but under intense conditions, you can generate NO. An electric spark can produce nitric oxide from nitrogen and oxygen gases in air. Nitric oxide has played many starring biochemical roles. In 1998, researchers received the Nobel Prize in Physiology or Medicine for discovering that the gas acts as a crucial signaling molecule in living cells. A few years later, it was approved to treat newborns with respiratory failure caused by high blood pressure in their lungs. Critical care and cardiac doctors also use NO off-label to treat acute respiratory distress syndrome and other types of acute lung injury and respiratory failure in adults. Okay, so that's worth reading about, I think, to see the mode of action for NO. All right, let's take a look. So what I wanted to show was some scientific papers, formal reports. These would be like a formal lab report that you would write. And there's so many posts here. I haven't checked here in a while. Chemist's Guide to Disinfectants. Disinfecting in 95 mass. It was probably near the beginning, so to go back. Go back to the beginning. All right, the link, I don't know where the link is. That's what I wanted to share with you for the papers. So if you're interested, you can also download the same papers. Let's see. All right, if I find the link, I'll end up sharing it with you guys, but right now I can't find the link. I thought it was going to be quick to find, but it's turning out to be a long time to search for that. But that was the quadruple bond. So the quadruple bond can obey the octet rule if there are no unshared electron pairs. There are multiple examples of the quadruple bonds. They just aren't very common, so that's why we don't see them in this chapter. 29, an atom X is bonded to another atom by a double bond. What is the largest number of additional atoms? Don't count the one to which it is already bonded, to which X may be bonded and still conform to the octet rule. What is the minimum number? Justify your answers. And so if we have an atom X, then we can do this. X can be double bonded to something, and then in order to maintain the octet rule, that's 4, so it can have 2 more. And so what we could have is 1 double bond and 2 single bonds, or we could have 2 double bonds like this. And so if it has, let's say A, B, C, if it has 1 double and 2 singles, then it could be bonded to 3. If it has 2 doubles, then it could be bonded to 2. And that would maintain an octet. An octet would have 8 electrons around X. 8 electrons around X here. And so it could be one or 3 atoms that it could be bonded to. Let's take a look. Oh, additional atoms, 2 additional atoms or 1 additional atom. If they're lone pairs, then if it has 2 lone pairs, then it might be bonded to no additional atoms. That could be it as well. A molecule contains a triple bond. Theoretically, there's a maximum minimum number of atoms that can then still obey the octet rule. So if we had a triple bond, then it can be bonded to 1 other atom or no other atoms if they're going to count 0. Triple bond. 1 additional. Now they're talking about maximum rather than additional. So I was answering it in terms of additional, but here the max is 2, and or none. Number of atoms in a molecule. So number of atoms in a molecule, not the atoms that it's bonded to. So it's jumping. It's just trying to be quick, but ended up being slower there. Because nitrogen has 5 valence electrons, it is sometimes difficult to fit a nitrogen atom into a Lewis diagram that obeys the octet rule. Why is this so? Well, 5 is an odd number. You know, octet is an even number, so that can account for it. Without actually drawing them, can you tell which of the following species do not have a Lewis diagram that satisfies the octet rule? So whenever you have an odd number of electrons, you can't satisfy the octet rule. This is going to have an even number because we have 2 nitrogens of 5. So 2 times 5 is 10 plus 6 is 16 electrons. However, this is going to be an odd number. 2 times 6 for the oxygens is 12 plus 5 is 17. So this has 17 electrons. So there's going to be an odd number of electrons. So it's probably not going to obey the octet rule. NF3, nitrogen is 5, fluorine 7. 3 times 7 is 21, plus 5 is 26. This is even. NO, that's 5 and 6, 11. That's odd. And so NO2 is going to have problems. Nitrogen dioxide. Nitric oxide is going to have problems. This is 3 times 6 is 18, plus 10 is 28. That's even. This is going to be even as well. 2 times 5 is 10. 4 times 6 is 24. Okay, chlorine 7 plus 5 is 12, plus 6 is 18. This is okay. Chlorine 7 plus 5 is 12. And so it'll make 12 and 12 is going to be 24, so that's okay. Okay. And so this is good. It's going to be this one and this one. Here. Okay, so odd numbers. What are the meanings of localized and delocalized when used to describe electrons in a compound? I haven't talked about this yet. I'm going to talk about this today, localized and delocalized. But it depends on what we call resonance forms. And let me talk about that right now. When we're looking at sulfur dioxide has a double bond, let's say on the left. single bond on the right. There's 3 lone pairs on this one. There's 2 lone pairs on this one here, and there's 1 lone pair on this sulfur here, like that. So when we're looking at sulfur dioxide, everything has an octet. There are some formal charges here. That is, this oxygen has 0 formal charge, but this oxygen over here has a negative formal charge, and this sulfur has a positive formal charge. Well, positive formal charge and negative formal charge neutralize each other, so the whole molecule is neutral. However, there's charge here on the atoms. Now, I drew the double bond on the left, but I could have drawn the double bond on the right, and so we end up with this alternative structure. This alternative structure is called a resonance form. And so we end up with 2 resonance forms like this, because it depends. If I drew the double bond on the left, I got this resonance form. If I draw the double bond on the right, I get this resonance form. Now, this is one of the problems with Lewis structures and that type of stuff. Lewis structures and this type of stuff, the problem is that I'm going to say, it's not accurate. One of the things we know is that double bonds are shorter than single bonds. And so what's happening here? Well, on the left, this bond should be shorter, this bond should be longer. On this resonance form, this bond's longer, this bond's shorter. And so which is it? And then the other thing is the sulfur's oxidation or formal charge doesn't change, but the oxygen does change. And so this oxygen goes from 0 to -1, and this one goes from -1 to 0. So which one is it? And so when we look at it, the reality is it's neither of these structures. And the reality of this is that the negative charge is smeared out over both these oxygens, and the double bond is smeared out over both of these bonds. Molecular orbitals and quantum mechanics, full quantum mechanical treatment doesn't suffer from this. And so we could see that if we build this real quick. Build this. So here's my sulfur, and then I'm going to throw in 2 oxygens on there. Throw in 1 oxygen there, and then 1 oxygen here. And then what I'm going to do is I'm going to make this oxygen a double bond. There. And so here I'm going to, let's have the double bond on the right here. Throw the double bond on the right. Okay, I'm going to, this is in their database. So what I'm going to do is I'm just going to replace it with the calculations already in their database. Sulfur dioxide, I cannot replace it with the calculations. Update molecules when names when replaced, replace it. All right, I can't replace it. So I'm going to set up the calculation here. We'll take a look. See how long this one takes. What's observed experimentally, and let me just tell you, that the bonds are both the same. The bonds are equivalent. The charges on the oxygens are the same. The bond lengths are the same. They're identical. You can't tell the difference between the 2 bonds on both sides of this. Calculations still going. Okay, it's completed. All right, let's take a look at the electrostatic potential map here. Just 1 second, let me do something real quick. George. All right, sorry about that. Let's take a look at the surface here. Now take a look at the surface. Do you see the two oxygens are identical in charge? You can't tell the difference. And then you can't see one of these bonds is shorter than the other. Let's go transparent here so we can see this. What is going on? Why is that not showing me the properties dialog box? Calculations. Maybe. Well, the point is that when we look at the sulfur is here, and the two oxygens are here. Sulfur is going to be positive because the blue is positive, and these are becoming more red. So they're orange, they're more negative, the oxygens. If you look at the negative charge here, they're both pretty equal. This is what's observed. This is the quantum mechanics. When we do Lewis structures, we get the wrong thing. Because when we do Lewis structures, we end up with, I deleted. Yeah, probably deleted. Unfortunately, I ended up deleting my drawings, but we end up with two resonance forms. Neither one is correct. And so what we have to do with the two resonance forms is we have to do an ad hoc thing, adjustment, because Lewis structures isn't enough. You know, the sulfur oxygen bond is longer, and then the charge is not 0, which would be green, and negative, which would be red. You know, it's not like that. And so we have the two resonance forms like this. And so what happens is we come up with a hybrid. And the hybrid is this. This left bond is either a double or a single. Well, what it is an average of the two. And so it's a 1.5 bond. And 1.5 bond would have the, rather than having a full line there, has a dotted line like that. And the same thing on the other side, that's kind of a 1.5 bond like that. And so the double bonding electrons get smeared out. Oops, this was not the right one here. Sorry, I jumped to this one too quickly. It's going to look like this instead. And so what we're going to do is we're going to come up with a hybrid. A hybrid is a mix, and in this case, it's going to be a 50-50 mix of both of these. So this is kind of an add-on to Lewis structures. It's because Lewis structures isn't the full quantum mechanical treatment. With the full quantum mechanical treatment, we wouldn't have to come up with the idea of the hybrid. The idea of the hybrid is it's going to be a 50-50 mix. So it's not a double, it's not a single, it's a 1.5 bond. And this was not a single, it's not a double, it's a 1.5 bond. So how do I show 1.5 bond? I'm going to show single bond to both, and then I'm going to dash. And so this is not a full double bond here. This is a half there. All right, now one of these oxygens is not 0 and then negative, and it's not negative and 0 here. These are going to be, the electrons are going to be smeared out. The extra electrons here are smeared out. And so this ends up being -1/2. And this oxygen ends up being -1/2 formal charge. And then the sulfur is still positive formal charge like that. And so what we get is we get a smeared out structure like that. And this is called localized bonding. You know, we have a double bond localized on the left here. This is called delocalized. That double bond's now delocalized over the left and right. And so that's what's that is what's meant by localized versus delocalized. What happens with Lewis structures is we get a localized structure like this that we have to delocalize using the hybrid. And the hybrid is an add-on method to Lewis structures to compensate for the fact that this does not describe reality. The reality is shown on the Spartan or on the other thing. So let me show you that. And so when we look at the experimental data, this is close to what we see. I mean, this is what we see experimentally. It's the same. So they say localized electrons are those that stay near a single atom or a pair of atoms. Delocalized electrons do not. Delocalized electrons get spread out, smeared. How would a particulate level illustration differ if you were to draw a calcium crystal instead of a potassium crystal? So take a look. Calcium crystal versus a potassium crystal. Well, you'd have calcium atoms instead of potassium atoms. It would look very similar. This is an odd answer. Calcium, I would think calcium metal, not calcium ion. Well, I think they're talking about the electron C model. And so calcium would have the 2+ pure pylons with 2 electrons floating in the ocean. Potassium would have the 1+ pure pilings with 1 electron per atom. And so that was the electron C model. Here, this would be for potassium. Calcium would have +2 and more electrons out in the ocean. So I think that's what they're talking about here, but I don't see it. It was in the PowerPoint. Okay, let's move on next. Are alloys pure substances or mixtures? Alloys are mixtures, you know, because the composition can vary. Compounds, the compositions are fixed. And so alloys are mixtures. They lack constant composition. You can vary the alloy composition a little bit by little bit. Bronze is an alloy of copper and tin. There's a bronze shoes there. What else do we got? Classify each of the following as true or false. A single bond between carbon and nitrogen is polar. That's true. You know, nitrogen is more electronegative, so it's going to make a polar bond. But what's the delta En? Well, carbon's at 2.5, nitrogen's 3.0, and so delta En's 0.5, which is borderline non-polar. But we'll call it polar. That's true. A bond between phosphorus and sulfur will be less polar than a bond between phosphorus and chlorine. Yeah, you know, we look at the periodic table for this one, and we look phosphorus and sulfur versus phosphorus and chlorine. So phosphorus and sulfur are going to have closer electronegativities. Chlorine is going to be more electronegative than sulfur, so the delta En is going to be bigger. The further apart they are, the bigger the delta En. The closer they are, the smaller the delta En. So phosphorus and chlorine, that would be true. The electronegativity of calcium is less than the electronegativity of aluminum. So you can look at the periodic table here. The highest electronegativity is fluorine. So let's look at aluminum, which is here, keep that in mind, versus calcium, which is here. And so calcium is in the next shell, plus it's to the left. And so 2 things going against it. One is in the next shell, so it's even bigger, so its electronegativity is going to be weaker. The smaller it is, the stronger it is. And 2 is to the left. And so that was true. Strontium ions are isoelectronic with bromide ions. So you can look at the periodic table to see. Strontium would be 36 electrons, strontium 2 plus. And bromide would be 36. So that's true. The monatomic ion formed by selenium is expected to be isoelectronic with a noble gas ion. Yes. Yeah, we expect that selenium should be, looking at the periodic table, 2 minus isoelectronic with krypton, 36. So we'll go from 34 to 36 electrons. That would be true. Most elements in group 4A, 14, do not normally form monatomic ions. It's the carbon family. And that's true. You know, monatomic ions would have, you know, carbon in the +4 or carbon in the -4, you know, as standalone. Although you might say, okay, carbon in the 4+, we don't necessarily see this, but we see this oxidation state all the time. You know, in carbonate, carbon dioxide, carbonate, all these have carbon in the 4+ oxidation state, but these are not standalone ions. One standalone ion might be carbide, you know, C4 minus is carbide, so silicon carbide, you know. But when you look at this silicon carbide deeper, it's not really, you know, there's a lot of covalent character to the bonding. It's not strictly 100% ionic. So there is some sharing there going on. Plus, you know, +4 and -4 are very high charges to sustain stably. So that's one other thing. So that's true. Multiple bonds can form only between atoms of the same element. That's false. Carbon monoxide, etc. If an atom is triple bonded to another, it may still form a bond with one additional atom. That's true, because triple bond, that's 6, we need an octet, so it could still form. An atom that conforms to the octet rule can bond to no more than 3 other atoms if one bond is a double bond. That's true. Electrons are localized between atoms in a metal. No. In metals, the electrons are totally delocalized in the ocean. We saw that over here. What was that? Oh, it was in the figure that I popped up here. But the ocean of electrons is delocalized. Delocalized means electrons are stuck in one place, but electrons in metals aren't stuck. Alloys are pure substances. That's false. Explain why ionic bonds are called electron transfer. Ionic bonds are formed by the transfer of electrons. Covalent bonds are sharing. This is a tug of war, you know, it has to do with electronegativities and delta En. And so there's a tug of war. Electrons. Compare the bond between potassium and chlorine and potassium chloride and the bond between 2 chlorine atoms. Well, potassium chloride is ionic. 2 chlorine atoms and chlorine gas is covalent. We don't write it like this. You know, the Lewis structure for potassium chloride has the potassium ions, the square brackets, and the chloride ions with the square brackets facing to one another. What is the electron configuration for the hydrogen ion? This one has 0 or nothing. You know, basically there's no electrons in hydrogen. So there's either nothing, no electron configuration, or we can start just saying there used to be, but now it's empty. So this is an empty orbital, but there are an infinite more, but this used to be occupied. So that's one thing we could do. There's other ways we could try to represent it as well. You're saying it has no electron configuration, that's fine. Identify the pairs among the following that are not isoelectronic. So we can just see, you know, neon and sodium from periodic table. There's neon. Neon's 10. Sodium ions 11 minus 1 is 10. So those are isoelectronic. And so we could just go through the periodic table and figure those out. Which orbitals of each atom overlap in forming a bond between bromine and oxygen? Which orbitals of each atom form? So bromine wants one. And so for bromine, if we want to use molecular orbital theory, it's too much, but we could use something called valence bond theory, which is going to involve, quantum mechanics. It's just quantum mechanics, the light version. And so if we look at bromine, we look at its valence, let's look at its valence electrons here. Bromine has the first shell, second shell, third shell, fourth shell. It's almost filled the fourth shell. There's just one electron short of filling the fourth shell. And so when I look at bromine here, I can look at how it's going to react. First shell's filled. Second shell's filled. Normally, people just write this because it's shorter. They don't write it all up, the quantum numbers. You should be able to write out all the quantum numbers for these orbitals. Third shell's filled. Fourth shell's almost filled. Each line represents an electron. Vertical line. And the 4p is almost filled. 4p is one electron short of being filled. Now, where's that one electron going to come from? An oxygen. It can come from oxygen here. And so it's going to be p orbital here. This is not a good example, unfortunately. Not the best example. And so bromine has 7 valence electrons, 1, 2, 3, 4, 5, 6, 7, and then oxygen has 6. And so oxygen is going to try to take this electron here from bromine. But bromine is going to resist a little bit. And so what we're going to do is we're going to form a single bond here, the oxygen here. That leaves oxygen wanting one more electron over here. And so if there's another bromine atom over here, then the oxygen can try to take that electron from that bromine and then bond another bromine to this. Get there, 2 bonds like that. Now, when we look at the bromine, it's going to be a 4p. And so we got the 4p orbital on bromine, only has 1 electron in there. It's a spin up. It's going to be bromine here. Now, we look at oxygen. Oxygen is going to be 1s2, 2s2, oops, 2s2, 2p4. That's 2p. So what we're going to have is on this side here, we have a bromine that wants one more electron. The way it's going to get an electron is by sharing an electron with a 2p orbital. 2p orbital is smaller than oxygen. And so what we're going to have to do is I'm going to have to flip this from spin up. I'm going to flip it to spin down instead. Yeah. And so that way we can pair it like this. And so I'm going to have a bromine. This is 2, 3, 4p. I'm going to have a 4p orbital on bromine overlap a 2p orbital on oxygen. Yeah. Okay. That's for one of the bonds. The other bond we have to do differently. The geometry, it's not going to be 180 like this. And so the other bromine doesn't come to this other lobe here. It goes to an entirely separate orbital over here. So we need an entirely separate orbital. I don't know why the book didn't get into this. They're asking questions in the homework about this. Another 2p. And so another bromine can come to this orbital here, overlap. 4p from bromine to 2p from oxygen. Is there any such thing as a completely nonpolar bond? Yeah, like hydrogen, you know, if it's a tie, like Cl2, H2, O2, it should be completely nonpolar. A bond between identical atoms is completely nonpolar. If you did not have an electronegativity table, could you predict the relative electronegativities of the elements whose positions are, yeah, which one has a higher electronegativity? Well, A is further close to fluorine, right? What about here? Yeah, this one's more tricky because on the one hand, it's higher up, so it's more electronegative. But on the other hand, it's further to the left, which means it's less electronegative. And so X is both more electronegative if it's higher up and less electronegative. So, but we don't know the relative, you know. And so XY would be hard to tell, but AB's for sure. No prediction can be made for XY. AB we can predict. All right, a monatomic ion with -2 charge has electron configuration. Actually, we've done so many of these electron configurations. Let me skip those. The bond, but you should do more if you need to build up your comfort level. But once you build up your comfort level to a certain point, you can skip it. The bond between a metal and non-metal is most apt to be ionic, whereas the bond between two non-metals, yeah, it's because of electronegativity difference. Metals way on the left, the non-metals way on the right, and so it's going to be a bigger electronegativity difference. Metals tend to lose electrons, non-metals tend to gain. A number of factors. Which bond, FSI or OP, is more polar? Okay, but do not look at the electronegativity. So we're only going to look at the periodic table, F versus silicon and O versus phosphorus. So looking at the periodic table, F versus silicon, well, fluorine's the most electronegative. Silicon's way out there. So this has a big difference in electronegativity, silicon and fluorine. Okay, versus oxygen and phosphorus. When we look at oxygen and phosphorus, they're much closer to one another than silicon and fluorine. So silicon and fluorine is going to have a bigger electronegative difference, and these ones are going to have a smaller electronegative difference because of their relative positions to one another. And so F and silicon are going to be more polar. F silicon more. There are two iodides of arsenic. So here we have arsenic in the +3 and arsenic in the +5. So arsenic triiodide and arsenic pentaiodide. A Lewis diagram that conforms the octet rule can be drawn for one of these, but not the other. Draw the diagram that is possible. From that diagram, see if you can figure out how the second molecule might be formed by covalent bonds, even though it violates the octet rule. Draw the Lewis structure for the second molecule. Okay, so the first one is definitely going to adhere to the octet rule. We got an arsenic here. Now, arsenic is in phosphorus, the group, it's going to have 5 valence electrons. 1, 2, 3. It's going to have 5 valence electrons. Now, if we can break up this lone pair into 2 singles, we can share additional electrons here. And so that's arsenic triiodide. With arsenic pentaiodide, what happens is this lone pair gets split up 2, and then 2 more iodines can come in and share. And then we have the other 3 iodines here. So this is going to violate the octet rule because we're going to have too many electrons around arsenic. And so we'll replace the bonding pair with a line, and then we'll get this. Let's take a look at the structure here. This is a violation of the octet rule because it's going to have more than the octet. So if I look at how many electrons are around arsenic here, there's 8 total around arsenic. 1 lone pair, that's 2, and 3 bonding pair, 2, 4, 6, 8. But when I look at arsenic pentaiodide, there are no lone pairs, and I got 2, 4, 6, 8, 10 electrons. So this is 10 electrons. This is 8 electrons. So 8 electrons is an octet. But this stuff exists. Arsenic pentaiodide exists. Okay, we'll look at the angles next chapter. So just why BF3 behaves as a molecular compound was AlF3 appears to be ionic. That's because the electronegativity, delta En is not as great. When we look at boron and fluorine versus aluminum and fluorine, that's what it should be. So we can take a look at the electronegativity table, Pauline's electronegativity table here. Do the Pauline's electronegativity table. I guess I didn't. Did I finish? I didn't finish my PowerPoint. Shoot. How about that? Maybe I did. Oh, I guess I did. Okay. So we're comparing BF3 with AlF3. So B is 2, fluorine's 4. So 4 minus 2 gives us delta En of 2. Delta En of 2 is polar covalent, borderline ionic. Al is 1.6, fluorine's 4, so it's going to be 2.4. 2.4 is in the ionic, the electronegativity difference. So fluorine has an easier time stripping all the electrons from aluminum, but it's going to be slightly more difficult to strip them off boron because of its electronegativity plus its smaller size. So that's what's happening with that. One explanation is that a boron atom is smaller than aluminum. All right. Okay, that's chapter 12. Let's move on to chapter 13. Take a look at the problems in chapter 13 here. I haven't been tracking. Is it? But Kazar probably knows. When is the next break time? Anybody? 10 minutes, okay, thanks. All right, let's draw the Lewis diagrams for each of the following sets of molecules. So there are different ways we draw Lewis diagrams. You know, different ways depending on what we're doing. For more complex ones, we follow a set of rules, the ones I wrote. For easier ones, we just look at the Lewis symbol. So for HI, that's one of the easier ones. We could just look at the Lewis symbol and we can see iodine's one short of an octet, hydrogen has one to give. But when we look at delta EN there, it's not going to be big enough to be ionic. So this is polar covalent here. So HI would look like that. The same thing with H2O. You know, we could just do this based on how many valence electrons we have here. And then oxygen wanting 8, so it's going to take 2 from the hydrogen, but it can't take them completely. So we end up forming polar covalent bonds like this. NCl3, nitrogen has 5 valence electrons like this, and chlorine needs just 1 more valence electron to complete its octet. And so, etc. And so we end up with this structure here, NCl3. There's a lone pair there. No, this is nothing. Here. Oops, there should be another chlorine here. Something like, as long as there's no formal charges, we can use this Lewis symbols. Now, once we get to charges, we can't do this. We have to be a little bit more careful when there's a charge present, you know. And so when the molecules become a bit more complex, what we'll do is we'll switch from using Lewis symbols, you know. You'd use Lewis symbols for simple ones. CO2. CO2 is probably still simple. Carbon has 4 valence electrons. Oxygen has 6. So oxygen is going to want 2 more. So oxygen is going to try to take this one and then try to take this one. And so we'll need 2 oxygens. So oxygen will try to take this one and try to take this one. And so when we form CO2, we end up with 2 double bonds like this. CO2. SF2, sulfur is like water, you know. There's the 6 valence electrons. Fluorine just wants 1. So we'll try to take this other one here. We got 2 of them. So we end up with a structure that looks like this. SF6 is going to have single bonds. It's not 180 like this. It's actually bent. It's actually a bent molecule. So we'll probably take a look at these structurally in more detail here. But probably should start doing it now. So take a look. At these shapes. Bromate, let's go, actually, let me do bromate. Now, bromate's going to get a bit complex. There's a charge there. If there's a charge there, then we don't want to do it the way we did it. And even here, it can be dangerous because you can end up with the wrong answer because we might not have a net charge, but there could be charges in the species, but they just cancel each other out. Those charges are going to be important in the structure. And so for bromate, we do it our standard procedure. Bromine has 7 valence electrons, 3 oxygens, each oxygen is 6, so that gives us 18 electrons. And then the -1 charge gives us 1 extra electron, +1. And so we end up with 26 electrons. And then we put the least negative species, which is bromine, you know, in the center. And then let's throw 3 oxygens maybe around it, like that. All right, that takes care of 2, 4, 6 electrons I've used so far. I have 20 more left, so I'm going to complete the octets to the terminal atoms. So that's 6, 2, 4, 6, 2, 4, 6, 2, 4, 6. And so I put on 6 times 3, I put in 18. I have 2 electrons left over. Any leftover electrons place on the center atom, like that. And so I get some structure that looks like this. Now, the bonding gets kind of screwed up. You know, when I look at bromine, you know, bromine likes to form 1 bond usually, like this. But if I split up some of these, I can make more bonds. That is, like this. Now, oxygen likes to form 2 bonds. Oxygen likes to form 2 single bonds or 1 double bond. And so oxygen likes to form a bridging oxygen or terminal oxygen. Okay, here it's terminal oxygen, but not with a double bond. It's terminal oxygen with a single bond. The bonding arrangement changes. Sometimes oxygen can form 3 bonds. Oxygen can form 3 bonds if it has a positive formal charge. And then oxygen sometimes can only form 1 bond if it has a negative charge, like that. Then we can see that type of arrangement. And so in this case, and then bromine likes to just form 1, but it can form up to 3 here as long as this formal charge changes. So when we look at the formal charges here, these oxygens all have the same formal charge of -1. And that's because if we count the electrons as 2, 4, 6, plus 1 is 7. And so that means that oxygen has 7. It's normally supposed to have 6, so it ends up with a negative formal charge. Now, bromine is supposed to have 7, but in this structure, it ends up with 2, 3, 4, 5. It ends up with 5. Bromine gets a +2 charge, formal charge. And so the bonding arrangement can change depending on the charge on the atom. So positive charge on oxygen means it can form 3 bonds. A negative charge is just forming 1 bond plus 3 lone pairs. All right, let's look at the structures now. This has an octet here, but the formal charge is a bit high. So we looked at the structure of water. It was bent or angular with a 109.5 undistorted and a 105 distorted. We looked at ammonia. Nitrogen trichloride is going to be very similar structurally to ammonia. So we'll do that one here. I already did water. The bond angle here is not 90. It looks like the bond angle here is 90, but it's not 90. It's 109.5. Now, this is going to have 4 groups. You know, it's going to have a lone pair group, a single bond group, a single bond group, and a single bond group. And so those are bonded to 3 chlorines here. Now, each chlorine is going to have three lone pairs. Okay. And so what is the structure? Well, the Mg for this is trigonal pyramidal. All right, okay, so it's break time. So let's take a break for 15 or so, and then we're gonna crank through these homeworks for chapter 13 after that. This time I won't I won't forget to mute the mic. You can come off the mic. If I'm not responding, come off the mic and then just give me a verbal. Because sometimes I don't see the chat window. Yeah, thanks for interrupting. Yeah, interrupt anytime. I forgot to record, yeah. So what I was saying, I just missed the first part, but the first part of this is these papers are available on the ACS site, American Chemical Society site, and they're free, so you can download them to your computer. There's a lot of them. And I don't know where the link is because they moved the link. It used to be right there on the home page, but it's no longer there. I think a lot of people took advantage of it. And so we have papers like this, which is a standard scientific paper. Again, standard scientific papers are going to follow a certain format. And certain format is, okay, we have the title, we got the authors, got the affiliations, you know, where they're from. And the abstract, again, is a one-paragraph summary, synopsis of the paper. Introduction is background, you know, history, what's going on now. Results are the results of the experimental. These are experimental results. And then they need to interpret the experimental results. And when they interpret the experimental results, that's called discussion. Experimental results are fact, you know. These are the facts of the experiment. But how do you interpret those facts? Well, that's discussion. Sometimes that interpretation changes. And so the results never change. The discussion might change, you know, once people get better insight or new discoveries come along. They might reinterpret the results, but the results never change because those are just the facts of the experiment. And so this is why we separate it into a results section and a discussion. Sometimes we discuss them together because there's not much, you know, to discuss and there's not much data collected. Conclusions are always a part of the discussion section usually. Sometimes they're separate. This is just what's the next step, you know, where should you go next? To summarize, okay, we demonstrate, we also proposed, you know, we believe that, you know, something like that. This is kind of a summary, but normal conclusions, they talk about the next step. And then we have appendix sections. Like, for example, if your experimental data is way too much, you know, then you can put that in an appendix. This is pretty detailed, you know, they talk about the chemicals. They got the chemicals from Sigma, Maybridge. They use 95% or higher purity. This is how they clone protein expression purification. These are all the mechanics of the experiment. This is way too much stuff to put in the main paper. All these experimental details are for others. And so they put these in the appendix. And there's so many different author affiliations that they put those in the appendix also. And then they have some supporting content here. Supporting information is available free of charge. Click that. See what kind of supporting information they had with the paper. So here. This is from the journal Medicinal Chemistry. All right, so I wanted to show that because our reports are not like this. At UCLA, the students had to write a report, abstract, introduction, results, and discussion for every experiment at UCLA. So they had to write like a mini formal report like this for every lab. The first one is a pain, you know, but once you get used to it, you know, like I had to do these as well. Once you get used to it, then it's not that bad, you know, to do. So if you do one, then you get more familiar with this and it becomes okay. So this is standard title, authors, affiliation, abstract, one paragraph synopsis, introduction, some background material, you know, 2019 novel coronavirus. Is a newly emerged human infectious coronavirus, etc. This one is a review, so there's not experimental, it's reviewing other people's papers, basically. And so this one, they didn't do any experimentation. They're just looking at the literature and reviewing the literature. And so the format of this one is not your standard format. You know, going from journal to journal, there are different formats. So that was a journal of medicinal chemistry. There are a whole bunch of those. If we look at biochemistry, let's take a look at that. It's going to follow maybe the same, like this is biochemistry journal. We've got the title, we got the authors, we got the affiliation, we have the abstract. The abstract is a 1-paragraph synopsis. And then the introduction. The introduction is, you know, background here. Now, this is the experimental section, which they labeled materials and methods. Materials and methods is the same as experimental. Here, there wasn't too much detail, so they have a lot more detail here. You know, they used, it looks like. And so the other authors put this in the appendix. These authors put it into the paper itself. Then they get the results. These are the experimental results. The materials and methods is just the equipment they used, the chemicals they used, you know, how they did it. The results were the results that we got from the experiments. This shouldn't change here. So these are all the experimental results. And then we go to the discussion. So the results are just the facts of the experiment. How you interpret those facts can vary. You know, this is your hypothesis in a way, you know. Here, let's look at their discussion. Bats have been found to harbor the largest natural genetic pools for new coronaviruses or coronaviral genes. The origin of a majority of the beta-cov coronaviruses could be traced back to bats. You know, but it's kind of interesting because there's a group in Australia. This group in Australia is looking for SARS-CoV-2 in bats at the markets in China and elsewhere. But they were unable to find it yet, you know, bats infected with SARS-CoV-2, which is odd because you'd expect, you know, if it's coming from bats, you'd expect that they could trap some bats from the wild and detect SARS-CoV-2. And so that leads them to other hypotheses, you know, the origin of SARS-CoV-2 in addition to some other observations that they saw. You know, but they should be able to trace this back to bats or some other animal. You know, it might not be bats, but it could have been from other animals. But they tested a whole bunch of animals that were sold at the market and still have not traced it. Well, that could have changed. That was a thing I saw a couple of weeks ago, 3 weeks ago or something. Okay, so we got the discussion. You notice there's no conclusion. The conclusion is always at the end, you know. At the end, sometimes they say where they need to go. And then some acknowledgements, appendices, references. That's it. So that's from Biochemistry, the journal. Let's take a look at Chem Reviews. Take a look at Chem Review here. Chemical reviews, again, this is a review. These guys didn't actually do any experimental work. They're just reviewing what other people have done up to this. You know, it's going to be a historical perspective of what's happened up to now. You know, and so this is a chemical review. This one is, wow, this one is preprint. Looks like it hasn't been published yet. And so, oh, actually it was published March 20th, 2020. This is peptide-based vaccines, current progress and future challenges, or peptide vaccine, cancer, treat cancer, Alzheimer's disease, and others. So here's the abstract and intro. Now, Chem Review is not going to have experimental section because they didn't do any experiments, basically. They're just looking at other people's, you know. other people's work and then just summarizing all the work up to a certain point. These are very useful for if you're going into a new field, you want all the review articles on that field because this will quickly bring you up to date on what's been done, historically up to this point. And so these are really useful. This Journal of Chemical Reviews is really good for learning new fields. And the other thing, textbooks are kind of far behind, for the like the leading edge of research, like this March 20th, 2020 stuff isn't going to make it in the textbooks for a while, And so textbooks are always far behind journal articles. So if you want, this is kind of the textbook presentation of, peptide vaccines, let's say, So Chem Reviews, that's really good. And then there are smaller journals. I have other journal articles, not from ACS. These are all American Chemical Society journals, but there are some journals that are totally free, that are sponsored. There's a lot of data came out of came out of different funding sources that are totally free. Use, but these ACS ones you have to pay to use, to access. Functional carbon quantum dots as medical countermeasures to human coronaviruses. This is applied materials and interfaces. So they're using quantum dots. In an abstract, they should always have numbers if possible. Numbers. That's better. This one is going to be your standard, introduction, so we got abstract, introduction. Okay, looks like, where did they put their experimental? Introduction. Maybe they didn't do any experimental. Maybe they're just looking at other people's work and results in discussion. Or maybe they're combining the experimental with the results. Here they're combining results and discussion. So for shorter papers, that's often done. Excuse me, since this is a shorter paper, they're probably combining everything, experimental results and discussion into one. And that would be the end. At the end of the discussion is when you kind of conclude if you have to, or they're having a separate conclusion. So the format of this journal is quite a bit different. Oh, here's the experimental. They put the experimental. So it depends. Applied Materials likes this format, and all Applied Materials papers will have the experimental at the end, and they should have a conclusion because that's the style of the journal. The style of the journal dictates how you write the article. Evidence of COVID-19 virus targeting the central nervous system, neurotropic mechanisms. So abstract, introduction. So they're giving you background on the novel COVID-19 virus. They're giving you background on the genome of the virus. They're giving you background on the tissue distribution of ACE2. ACE2 is where the virus attaches. This is the hypothesis of MedCram. The virus attaches to ACE2, and that screws up the angiotensin 1, 2, and 7 ratio, which screws up, which causes more superoxide, which does this and does that. ACE2 is in the human brain. So the virus can mess with your neurological function. How the ACE2 receptor is exploited. So this is giving you really good background information, on this. A proposed cascade of cerebral involvement in COVID-19. So this is showing how SARS-CoV-2 is impacting your brain function here. The conclusions of future directions. Conclusions always include future direction, where you need to go, what the next steps are. So let's see what they say. as far as future direction goes. Okay, here. Often you see this, which needs to be further elucidated, you know, so these are unanswered questions that need to be answered, you know, these types of things. Urgent need to understand the neurotropic potential. Kind of stuff. ACS Journal of Infectious Diseases. It's limited time. Limited time, it's going to be free. So we have authors, title, authors, affiliation, abstract, intracellular pathogens with repurposed host target drugs. So repurposing drugs. A little bit of introduction gives you the background, you know, some history about this. All right, this is more of a review article. So they don't talk about any experimental work they did. They're just looking at a review. More ACS Nano. Let's see what that one is. Cell membrane mimicking nano decoys. Sarah. All right, so check those out if you're interested. There's one other thing. I don't know if I mentioned, did I mention this? That fall, I think I already did. Fall is going to be entirely online. Have you guys heard that? At El Camino. Fall will be entirely online. I was pretty disappointed about that, but you know, I guess it's best to be safe than sorry, but you know, what that means is that we're going to be online until a vaccine comes about. And you know, people have been trying to develop a vaccine for a lot of drugs and they haven't been successful. Like HIV, you know, AIDS. They've been trying to develop a vaccine for that. Right now they have effective treatments for it, so that's good, you know, and then they have things that can lower your risk, but still there's no vaccine, you know. And so they've been trying to make vaccines for a lot of things, but have not been successful. A vaccine for, they're trying to make a vaccine for SARS, you know, original SARS virus, MERS, Ebola, you know, lots of viruses out there. So hopefully, you know, it's going to stage 3, whatever, trials. So hopefully it works out. Let's see here. I do here. I forgot. I signed up for MedCram because YouTube, every video that he did with hydroxychloroquine, YouTube deleted from it. So there are a whole bunch of videos that were missing. So I ended up joining MedCram because then I could watch the ones that were deleted by YouTube. YouTube has since put those videos back up. So now you can watch the videos on hydroxychloroquine back on YouTube. But for a while, you couldn't watch any videos on hydroxychloroquine because that was one of those ones that they called false information or something like that. So this is that thing I posted on Piazza, but this was on update 98 here. And so this is kind of interesting because normally when we have a test, we'd like the test to be 100% accurate, but what does that mean? You know, maybe the test is, in a way, the ones that have a high degree of accuracy are catching non-infectious people too. So maybe we don't want that, you know. What we want is more of a targeted accuracy. And so this is a very interesting thing on this and how to get, because if we have to wait for a vaccine, how long is it going to be? It's not just going to be fall, it's going to be spring too, because it's going to take time. You know, let's say those stage 3 trials are successful. It's going to take time before it goes into full scale manufacturing. And so by that time, it means, you know, spring is going to be all online too, because of course it's better to be safe than sorry. Therefore, spring is going to be, and that means next summer is going to be, you know, so when is the lockdown going to end? Well, it's going to end with a vaccine. Otherwise, it's never going to be safe. Now, when is it going to be safe enough to go back to school? And so this professor at Harvard, he's maybe hypothesizing that maybe it's okay to start going now, you know, based on this. So let's look at some excerpts from this.
One of the things that a lot of people are thinking about lately is getting back to school. And of course, this is a big topic about whether or not it's safe to go back to school. We're not going to weigh in on that today, but what we are going to weigh in on today is a new idea that might make going back to school more of a reality. And that has to do with testing. And I want to thank the folks over at This Week in Virology, which put together a great podcast that they do every week. And we'll put a link in the description below to their podcast. And this last week, they had someone on from Harvard to discuss a new idea that I think may actually be a step in the right direction. And the question really boils down to testing. Do we need better tests? Or do we need more of tests that maybe aren't so good, but just more of them? And that's really where the question boils down to. And it's a really important question, especially now that we've essentially inundated our current testing capabilities. And we'll get more to that. But before we do, we've got to sort of review a little bit about how the virus behaves and some of the numbers that we use to track it. So let's talk about that first. So there was this paper that was published in the New England Journal of Medicine that looked at SARS-CoV viral loads in upper respiratory specimens of infected patients. And I want you to notice something here. These are all different patients, and they're looking at, for instance, nasal swabs, throat swabs, and then they looked at something called the aggregated CT value. So this is something that's really important that I want you to understand. Here are the days since onset of symptoms on the x-axis, starting off at 0. And then they have something called the CT value. So the CT value is a way of measuring the viral load. And for every 3, if you went from 40 down to 37, that's a movement of 3 points on the CT value. And you're actually going down in value from 40 to 37. But that movement of 3 actually translates into a 10-fold increase. That's right, increase in the viral load. And so in fact, CT values are inversely proportional to viral loads. As you go down in CT value, you go up in viral load. And so if you were to move about 9 to 10 points, that would be 3 times 3. And so that would be not 10, not 100, but 1,000 times larger. So you can see it going from a viral load that's very, very low here at 40, going to a viral load perhaps in the billions or even trillions as you get up to 15, 10, or 5. So
that's a logarithmic scale, or powers of 10. That's why.
Something to keep in mind, that CT values that are low mean that there's a lot of virus particles. And CT values that are down here in the 40 range are almost undetectable. I bring that up so you can understand, because the rest of the discussion is going to be around these CT values. So let's take a look at the natural history of a virus, specifically coronavirus in this case. What typically happens is the virus starts infecting and there is exponential growth. And then as it tapers off, viral particles can actually last for some period of time before they taper off to 0. And again, those CT values, this would be around 40. We can go all the way up to 5 up here. I think the key number that we're going to need to look at here is around 35. And of course, that can go up. And these are approximate values. What we have right now is we have something called reverse transcriptase PCR, RT-PCR. And we're going to put that in green. Now, real-time PCR or reverse transcriptase PCR is pretty expensive, the gold standard stuff. It's about $100 a test. Right now, we're experiencing pretty long turnaround times, anywhere from 3 to 4 days, all the way up to, I've seen it as high as 9 days to get that test back. And there's not that many of them, but it's very sensitive. Let's say, just for argument's sake, it's around 35 CT values. So that means it can detect all the way down to 35, or even as low as 40. That means that we're able to detect using reverse transcriptase PCR all the way out to here. And so all of these patients, if they were to test, would test positive on this test. Now, apparently, there are some tests that are known as paper tests. And apparently, all you need to do with these paper tests, because they're paper coated with monoclonal antibodies that can detect antigens, they're not detecting actual RNA, but antigens. These are more along the lines of $1 to $2 each, but they're not as sensitive. Some would say that they're maybe even 50% sensitive. Now, it's not a random 50% sensitive. No, it's maybe somewhere in this range. So that this is the range of people that we're talking about. So in other words, here to here, and the CT level that we're talking about is in the low 30s. And these numbers may be a little bit different, but you're getting the idea of what I'm talking about. One of the things that has been made clear to me is that the threshold of transmissibility is actually more narrow than we thought it was. Well, this is exactly what Dr. Mina from the T.H. Chan School of Public Health at Harvard University was making a point of on This Week in Virology.
So people who are transmitting probably have CT values that are below 30, and the vast majority probably have them below 25 or so.
How do we know that? Do we have evidence that people are still positive, but they're not transmitting the virus? And the answer to that is yes. If you look back at one of our updates, we highlighted a South Korean study where these people that kept on testing positive were checked. And they looked at household members and they were found not to be infective. In fact, they did background checks on these patients and found that not a single case of transmissibility occurred in these patients that were persistently positive. And the reason is because the nature of this test, RT-PCR, is you're looking for fragments of RNA. And fragments of RNA, while they will turn the test positive, fragments of RNA are not enough to actually cause transmissibility.
A lot of people are saying, well, we need the really sensitive tests to be able to detect people early on in their infection. but almost all of the time that people spend with this virus near the limit of detection of PCR is on the tail end of their infection. This is a virus that once it hits PCR positivity levels, it's growing well in its exponential phase, and it's probably a matter of hours, not days, before it passes the threshold to be detected on some of these slightly lower sensitivity assays. And then it will sort of persist for weeks potentially, or months even in some people at very low RNA levels. So it's after people are well beyond their transmissible period that we're actually seeing the loss in sensitivity of these assays. It's very rare that you actually detect somebody with a CT value of 39 in that window on their way up, because they're only sitting there for a few hours before they get down to a 33. So if you're missing CT values of 39, in my perspective, who cares? It's really not that important.
And so the point here is that, yes, these tests here may actually be maybe 50% sensitive, but in comparison to what? It's in comparison to a test that may be overly sensitive. And so in fact, the question is if your threshold of transmissibility is closer to this threshold of actually being positive on these much cheaper tests, these are tests that can be repeated on a daily basis. And so these tests may actually be more beneficial in terms of controlling an outbreak of the virus because you're able to do it more quickly. And by the way, there's one thing I forgot to put down on here. You get the results back in 10 minutes. You can have them at home. You can test serially, maybe once a day, maybe twice a week, 3 times a week. And if your child is positive, then you hold them back from going to school. If they're negative, they go to school. And you have real-time application of this.
So he was mentioning that from at the onset, you know, those tests aren't going to detect these people at the onset, but the time frame, because it's exponential here, is only a couple of hours or maybe 3 hours, you know, from the time where their levels, let's say below detection limit to the level at detection limit. Versus over here, so most of the people they're catching, let's say above the low 30s, is already past, you know, they're already recovering from the virus itself. So this totally makes sense, having a test like here that's a little less sensitive. It's not going to catch these people on the leading edge, but, you know, in an hour or two, it'll catch them versus catching all these people who have already passed.
What the CDC's most recent announcement, maybe it was last week, 9 out of 10 people go undiagnosed with this virus today in the US. I would say that of those 1 out of 10 that do get diagnosed, almost all of them are getting diagnosed through surveillance after they've been infectious. Because their CT values, we've seen the average CT value kind of creep up to 35 or so. So that means they're almost all at the tail end. So what that tells me is if we take a step back and we look at this virus and our testing program in the States, we're using a very sensitive test, but our sensitivity to detect infections is probably below 5%, you know, across the US right now. The CDC says it's 10. And if we actually say detecting transmissible infections, we're woefully underutilizing testing. So if we know that the virus transmits once people are above, say, 100,000 or a million copies per mil, then maybe we only need a really crappy test if we can use it, if it's cheap enough to use it very frequently. Then it doesn't detect less than 5% of people when they're transmitting. Maybe it detects 85% of people when they're transmitting. And that's a huge win over what we have right now.
And if you want to read the preprint of Dr. Mina's work, we'll have a link to its PDF in our description below. I think he makes a good case for this, and I'd like you to read it for yourself.
To me, the short way to say it is, if the test isn't as good, but we do it every day and you get the results quicker, you're going to be way ahead in the long run. I mean, that's the other thing we haven't really touched on is the turnaround time, but the sensitivity, okay, maybe not perfect, but test every day, get the results quickly. And if you test wrong the day 1 on day 2, you'll probably test positive. you know.
That's exactly right. And on aggregate, you'll drive the R effective, of this virus way down below 1. I mean, I think if you were to take this and give everyone in Miami or Austin or wherever they're burgeoning outbreaks right now, give everyone a test or give 50% of the people a test, you'd probably drive R effective down overnight. If everyone tomorrow could wake up, test themselves, you'd immediately filter out tens of thousands of people potentially who have the virus in them that day. And the other consequence is you don't have to worry about contact tracing because everyone would be doing their own test every day. It just, it can be done. And
this is with a pinprick, right, for a little bit of blood.
No, this is with that's a different thing which I could talk about is the serology bit. But no, this is actually just kind of spitting on a paper strip or taking a Q-tip and putting it into a little plastic tube of saline and dropping a paper strip in there.
I'm thinking about school kids. You get up in the morning and take the test, it tells you whether or not to go to school. That solves the whole problem.
Yep. And it doesn't need to be perfect. You have one kid who tests negative and, they actually go to school. Well, that kid, otherwise that kid's not going to get tested at all, so they'll find themselves positive the next day and they'll infect overall fewer people, and anyone that they infect will on average find that they have been infected and they'll stay home. So it very quickly compounds into a massive reduction of virus in the population very quickly. The FDA and the CDC and the NIH have to change their messaging. They have to say, look, there is actually a technology that a test could exist right now. I have some sitting in my office next to me. They're paper strips. They're just little pieces of cardboard printed with monoclonal antibodies that can pick up an antigen. It's essentially a lateral flow assay. It can be printed in the millions.
And you may be thinking, well, why didn't these tests come out earlier? Well, in fact, they did, but they were kind of beat up because of the low sensitivity. And this is the paper that did the beating up. This was at a New York University Grossman School of Medicine. And if you go to the end of this print, you can see some of the things that were highlighted in terms of which tests had negative results when the RT-PCR had positive results. And you can see here the sensitivity of this test called the Abbott ID Now, which is one of these cheap tests that can get done pretty quickly. It had a sensitivity of only 51.6%. But again, as we showed, the 51% sensitivity was not just a random 51%. The tests that it missed were probably those patients that were past their infectivity in terms of CT values. And more specifically, what is it going to help somebody if it takes 8 or 9 days to get back a very accurate test, but now they can't do anything about the results? Here, this is a very quick test. You get it back in 10 minutes. And as you can see here, the positive predictive value was 94.1%, which of course would change based on the prevalence. But if you look at some of these tests that were done, you can see here that we have the Cepheid result, which is the gold standard in this case, and then you have the Abbott ID Now result, which had the lower sensitivity. If you see here, this was negative when this was positive. What kind of a test result is it being missed on? It's looking at the nuclear capsid CT, which is around 43. That's an extremely low viral count and probably not going to make a big difference in terms of whether that patient's isolated or not. Here is another one at 40.7. Again, not a big difference. That's such a low viral load. Here, 44. Here's another one, 44.3. Here's another one at 36.3. Whereas you can see the higher viral load counts based on the lower CT numbers, 29.7, 27.6, 19.7, 18.6. It's all picking these up. And so what you have here potentially is a test like this that's pretty cheap that you could pick up, you could test daily, find out whether you're infected. And if you were, you could stay home and prevent infection to other people. This may be a way, potentially, to get out and get kids back to school, which is obviously the ideal situation. One of the reasons that Dr. Mina points out that the reason why we're not seeing these as much is because these companies may be having a little bit of difficulty in terms of thinking that they're going to get this past FDA approval because the FDA really wants to have some rigid standards in terms of how accurate the test is going to be. And if they're working on that, it's going to raise the price of these tests. And they believe that if there is a viral particle in the patient, the test should turn positive, when in fact, the practical definition of what we're really looking for here, when we're trying to curb an outbreak, is who is infective and who is not infective. And that may be a completely different question than who has the viral particle and who doesn't have the viral particle. Ideally, what you want is a very cheap test that everybody can self-administer, that is widely available, that will tell you whether or not you're infective. Thanks for joining us.
All right, so you can see where it failed, and going back here, where it's going to fail with those low the high CT numbers. I mean, the viral loads, especially post, if it's post rather than leading here, it's well past the infectious stage. Here, though, it would be, you know, if they just became infected and the viral load is increasing, then it's a different story. But, you know, this is, like he was saying, timeline, a few hours. And so it's something that there is a little bit of risk on the leading edge, but not on the tailing edge. On the tailing edge, these people, and there have been papers published here that are reviewed showing that, you know, these people who are testing positive here are not infectious. They're family members who are not getting sick from people with these low viral loads, and testing, and they had tested positive for it. So this is very interesting, and so this is why that next talk is coming in August 5th next week. You might be interested in checking out the recording of that, but that's going to be during our class time, so we aren't going to be able to watch that. Unfortunately, it'd be interesting and to hear, you know, and I wonder how big of a risk this is. You know, what fraction of people would fit, you know, just based on statistical analysis, you know, what kind of risk do we have on the leading edge here? Okay, let's move on here.
This is.
But that was interesting. I mean, we got to start thinking, because right now, to me, it seems like the strategy is wait until a vaccine comes out. But that's always risky, because what if a safe vaccine doesn't come out? You know, people have been waiting for vaccines for decades. And it's not so easy to do, but, you know, obviously a lot of people are optimistic, like Dr. Fauci was very optimistic that the vaccine, he's not if a vaccine comes out, he's saying when a vaccine comes out. But even then, when a vaccine comes out, when is that, you know? Is it a year, 6 months, or a decade from now, you know? And so you got to start thinking of a plan B, you know, right now the plan A is to wait for the vaccine. At least that's what it appears to be. So let's go back to this. So I got sidetracked there, but I mean, I've been wanting to show that anyway for a bit. Okay, so we are not, that's over in place here. Okay, so we're looking at NCL, which is trigonal pyramidal in shape. And so let's take a look at that. The polarity of NCL is quite a bit different than the polarity of ammonia. Even though this kind of looks like ammonia, is of the shape, you know, it's ammonia-like shape. It's quite a bit different, because rather than having hydrogens, having chlorines bonded to this makes the whole dynamic quite a bit different. So one, the polarity, you know, when we compare this to ammonia, the polarity is inverted. That is, when we look at ammonia, you know, the nitrogen here is delta minus here. Because hydrogen's less electronegative. So this would be colored blue in the electrostatic map, or I'm not blue, red. Red is negative in the electrostatic map. And the hydrogens would be blue here. And so we built this yesterday. But this would be flipped around. In this case, the chlorines would now be red here. Because chlorine's more well, actually, is it? Well, chlorine's going to put up much more of a fight. You know, nitrogen's more electronegative, but chlorine's going to put up a significantly stronger fight. And so this is going to be tough to determine, because when we look at the Pauling's electronegativities, which you can here, and we compare chlorine with nitrogen, you know, nitrogen's a 3O, chlorine's a 3,2, but nitrogen's smaller. And so the three most electronegative are nitrogen, oxygen, fluorine, but this is really close. We don't know. So this is hard to tell. Now, normally I would say chlorine's more electronegative because it's a halogen. And so I would have inverted this as far as oxidation states. When we do oxidation states, that's what we end up getting. Let me show you what we end up getting with oxidation states here. With oxidation states, we assign, you know, I'm going to keep these as delta negative here. With oxidation states, we assign chlorine -1. Chlorine goes first, and -1 is a halogen. And that would leave nitrogen at +3. Well, if that's the case, nitrogen went from electron rich, because this is nitrogen -3, and the hydrogens are +1. And so it's inverted. You see, nitrogen was electron rich, now it's electron poor. +3. And so this nitrogen is going to be much, much more blue. This nitrogen is quite red here. And then we have these. If we use the electronegativity straight, then it goes in line with our oxidation states. So that makes the chlorines negative and the nitrogen positive, okay, like that. And so this was like, we saw this with what was that called? Fluorosil. Anyway, in the video on structure and health, they ended up replacing a hydrogen with a fluorine. And so hydrogen with a fluorine, this is in the molecule uracil. And this was fluorouracil. And so when you replace a fluorine there, it's going to flip the charge. And so this one is pretty much non-polar, really quite non-polar. Actually, it's a bonded to carbon. I'll have to check that. I think it was uracil. And so hydrogen is a lot less electronegative than that, but fluorine is much more electronegative. So all of a sudden, we're going from a tiny, tiny delta plus here to a large delta minus. And so the whole electronic environment is flipped a bit. And so this is one of the reasons why, you know, this could be disruptive towards the enzyme, you know, once it's in the enzyme there. These are almost negligible. Carbon-hydrogen bonds, non-polar, pretty much we say. But in fluorouracil, it's been flipped like that. This is kind of the same thing. It's been flipped. So this is a good fuel. This is not a good fuel. You know, you can burn ammonia. You probably can't burn this nitrogen trichloride is probably not going to burn. And so this is what we get. This is what we get from Lewis structure analysis. You know, let's take a look quickly at building something like this and seeing what it looks like here compared to ammonia. I think I should have ammonia still. So we got the nitrogen trichloride. Let me see if that's in the database. It's not in the database. and set up. Okay, let's let that go on here. Okay, as that's calculating, let's move on to some of the other structures and take a look out here. All right, now CO2, you know, actually we did these already. CO2, we have to form double bonds. SF2 did that. Okay, let's take a look at these. Hypobromite, we have dihydrogen phosphate and chlorate. Let's see how we're going to handle these ones here. And so these are ions. So probably best to do these using the rules that we talked about. So this completed. And so let's see how the polarity changed. You know, in ammonia, nitrogen was negative, so it was red. Let's see in this case, nitrogen is like here. Do you see in this case, it's not nearly as red. Not nearly as red. And so it's more, as the red color is gone, it's getting more green, but the chlorines here are still blue. So this is telling me nitrogen, you know, because blue means positive, so the chlorines are positive. And so this is telling me that nitrogen is more electronegative because it's sucking more of the electron density away from chlorine. So the numbers there aren't totally accurate, the numbers in the Pauling's table, you know, those are just, you have to use those, realizing that there are some exceptions to those. And this is why I say, even though ignore the numbers, nitrogen, oxygen, and fluorine are the three most electronegative. And so what that means is that these are slightly, draw that. That means that these are, you know, blue is positive. I guess I can't write on there, can I? Let's see if I can write. Can I write? Oh no. Unfortunately, I can't. I thought I did earlier. Try one more time here. Oh, actually, you guys can't see. Can you see what I'm looking at? Okay, this is nitrogen trifluoride here. And again, you can see the trichloride. You can see the chlorines are blue here, indicating positive. And the red, nitrogen used to be red, but it's a lot less red. And so chlorine's putting up more of a fight, but it's not a total fight here. I mean, let's see. Go back to this. Let me do something really quick here. That's not what I wanted. So when we look at ammonia, and compare, it's quite a bit more red on the nitrogen and quite a bit more blue on the hydrogens here. Chlorine obviously is going to put up a lot bigger fight in this particular instance here. So there we go. Okay, I guess I lost it. I was going to try to put two on the same page, but it didn't work. And so, and make a long story short, nitrogen's more electronegative than chlorine. Or nitrogen is more electronegative than chlorine, although chlorine has a higher electronegativity number, 3.2. And it's largely thought to be the size. And so this is thought to be less. And so the order would be fluorine, oxygen, nitrogen, chlorine, bromine. All right, going back to this, okay, so these are ions. For ions, we want to build them following the set of rules. And the set of rules is just the steps. So sum up the valence electrons. Bromine normally has 7 valence electrons. Oxygen normally has 6 valence electrons. And then we have the negative charge. The negative charge, -1, is 1 extra electron. And so that's 7 and 7, this gives us 14 electrons total. And so we have bromine and oxygen, just 2 atoms, so we'll just connect it with a bond like that. And then we have extra electrons. Now, with the extra electrons, because we've only used 2 of the 14, so that leaves us with 12 electrons. So what we're going to do is we're going to complete the octet to the more electronegative atom. Oxygen is more electronegative, so it's going to get the electrons first. And then leftovers will go on the less electronegative atom. And so bromine was going to have, let's see, how many would we use? 2, 4, 6, 8, 10, 12, 14. So bromine ends up getting an octet as well. Both of these have an octet. That is a total of 8 surrounding this one and a total of 8 surrounding this one. Okay, so this would be hypobromite. Now what we have to do is we look at the formal charges next. You know, the formal charge here, we count up bromine. It's got 2, 4, 6 that belong entirely to it, and then it's going to have half of these, so it gets 7. So bromine normally has 7. This is valence, minus 7 in the structure gives us a formal charge of 0. The formal charge of that, 0. Oxygen has 2, 4, 6, 7, half of the bonding. Oxygen normally has 6, and this structure has 7, so it's going to have a -1 formal charge. And so the -1 formal charge goes like this, and this whole thing has a net charge of -1. All 2-atom species are linear, no matter what. This is linear, you know, 2-atom species. Now this one's very tricky here, because how do we do this? So for example, if we did phosphorus and then 2 hydrogens like that, and then 4 oxygens like this, it would look weird. You know, this is going to have, phosphorus is going to have more than an octet, 2, 4, 6, 8, 10, 12. It's possible that phosphorus can have more than an octet, but one of the things is this: for acids and acid anions, the hydrogen, the acidic hydrogens are bonded to the most electronegative atom. The most electronegative atoms, if we have more than one. And so it's not like this. If I have that, because the hydrogens are bonded to phosphorus here, if this is an acid, the hydrogen should be bonded to the oxygens because the oxygens are more electronegative. And so it might be a situation like this where I have a phosphorus with 4 oxygens. That gives me an octet around phosphorus, that's fine. And then bond the hydrogens to the oxygens like this. It doesn't matter which 2 you pick. You know, either is fine. Okay, now how many electrons have I used? So let's do an electron count here. So I have 2 hydrogens, that's 2 electrons. And then I have 1 phosphorus. Phosphorus is 5 valence electrons. And then I have 4 oxygens. Each oxygen has 6, so 4 times 6 is 24 electrons. And then I have a -1 charge, which is 1 extra electron. And so that gives me 25, 30, 32 electrons total. So how many have I used in the structure? I've used 2, 4, 6, 8, 10, 12. So I have extra electrons left over. And so what we're going to do is we're going to complete the octet. So I'm going to complete the octets to the terminal oxygens. This is called a bridging oxygen. I'm going to complete the octets to the terminal oxygens first. So that's an octet there. That would be an octet there. Now how many have I used? So 2, 4, 6, 8, 10. 2, 4, 6, 8, so 18, 20, 22, 24, 26. So I still have 6 electrons left over. So we'll put the bridging oxygens here. Oh, maybe I have 8 left over here. Let me see, does that work? So I have 8 plus 8 plus 8 plus 8. So 4 times 8 is 32. So this is 32 electrons here. 2 electrons. But I have some formal charges here. Now, the hydrogen is going to be 0, gets 1 electron. This oxygen, bridging oxygen, is going to be 0. However, these terminal oxygens are not. That's 2, 4, 6, 8. It should have 6, so it has 2 extra electrons, which is minus 2. This one is 2, 4, 6, 8. It should have 6. It's got 2 extra electrons, is minus 2. Phosphorus, how many does that have? Well, that's going to have 1, 2, 3, 4. Phosphorus is supposed to have 5. So this is going to give it a plus. These are formal charges. Formal charges I circle, oxidation states are in parentheses. Formal charges are encircled. This. So I have minus 2 is minus 4, plus 1 is minus 3. So this whole thing carries a, is that right? That's not right. It's not, so minus 1, sorry, this is minus 1, and this is minus 1. So minus 1 and minus 1 is minus 2, plus 1 is minus. So this is dihydrogen phosphate here. Now, what is the three-dimensional structure of dihydrogen phosphate? So let's take a look at that next. Three-dimensional. So when we do that, we look at like the phosphorus center and then the oxygens and this oxygen. Now this phosphorus has 4 groups, single bond, single bond, single bond, single bond. That's 4 groups. And when we have 4 groups, the lowest energy arrangement of 4 groups is a tetrahedral. And so what I'm going to do is I'm going to put phosphorus here and then do a tetrahedral of single bonds. This. Now I'm going to put, let's see, I'm going to put the bridging in the plane. That'll make it easier to draw. And then these ones I'm going to make the terminals. And so the terminals I'll make out of plane like this. And the bridging I'll make in plane like this. So I'm going to have an oxygen. Now this oxygen is also going to be tetrahedral. It's also going to be tetrahedral because it's got 4 groups, 2 single bonds and 2 lone pairs. And so this is the way I'm going to do it. I'm going to put 2 of the groups in the plane. Tetrahedral has 2 in the plane, 1 coming out like this and 1 going in like that. Now the 1 coming out is a lone pair. Now this wedge represents a pair of electrons, so I was a little bit too quick to do that. I don't normally show lone pairs as wedges and dashes. Instead, the way I show lone pairs is if a lone pair is sticking out, I'm going to make it bold like this. If a lone pair is sticking in, I'll dot it like this. And so this is my wedge lone pair coming out. This is the dash lone pair going in. And so I'm going to do the same thing up here. I'm going to do it. And this is going to bridge to hydrogen. So which way should I do it? In this case, I'll tweak the hydrogen the opposite direction. And then I'll wedge out 1 lone pair, making it bold like this. And then dash in 1 lone pair by making it dotted like this. And so I see that as tetrahedral. The way I see that as tetrahedral is I have a wedge coming out like this. I have a dash going in like that. And then I have a bond coming down like this and a bond going out like this. And so this ends up being a tetrahedral EPG. I have 4 groups here. It's a tetrahedral EPG. This group sticks out, so I can do 4 balloons. This balloon goes in here. And that would be it. It's a tetrahedral EPVG, but it's bent Mg. Because if I look at the bonded atoms, you know, I have a hydrogen bonded up here and the phosphorus bonded here. So if I look at the bonded atoms are going to form a bent or angular shape. And this bent or angular shape should be a 109 angle. But we expect it to be distorted because lone pairs take up space. And so when we're doing the geometry of this, we do it like this here. That phosphorus is going to have an EPG, that's tetrahedral. It's going to have an Mg. Mg, it's got 4 bonded atoms, so it's also tetrahedral. And the angle, the OPO angle, is going to be 109.5 degrees. Now, these oxygens are, this oxygen is going to have an EPG that's going to be tetrahedral. It's going to have an Mg that's going to be bent. And the angle here, the HOP angle, we expect to be 109.5 degrees. But we expect some distortions. The reason we expect some distortions are lone pairs. Lone pairs are more repulsive than bonding pairs. And so we expect it to be distorted to about, we'll get 2 lone pairs, so about 2 degrees distortion per lone pair, so maybe about 105. So about 105 degrees for that angle. Now, this is the same. You know, these 2 oxygens are the same. There. Terminal atoms, we don't do that for, so I wouldn't say anything about the hydrogen. You know, it's center atoms. In this case, we have 2 central atoms. One is phosphorus, the other is oxygen. So this is why we have this type of situation here. Okay, that was dihydrogen phosphate here. Okay, let's go to chlorate. Now in Chem 1A, you're going to learn something about expanded octets. Sometimes formal charges are, we try to minimize the formal charges in this case. And sometimes we can minimize the formal charges by forming double bonds. But we'll leave that for Chem 1A. Let's look at chlorate here. And so the procedure is sum up the valence electrons and charge. Chlorine has 7 electrons. 4 oxygens, each oxygen is 6, so that's going to be 24 electrons. -1 charge is 1 electron. 25 and 7 is 32 electrons together. Now, the least electronated goes in the center, that would be chlorine, and then we'll have the oxygens around that. So Lewis structure might look like this. Okay. Now, how many electrons have we used? So 2, 4, 6, 8. 8 for this basic structure, and so we have more electrons to go. So what we're going to do is we're going to complete the octets to the terminal atoms. So we need 6 more each. And so that gives us 32 electrons, you know, because it's 2, 4, 6, 8 times 4 is 32 electrons. So that checks out. Now, what are the formal charges in this particular thing? And so when we have this type of oxygen scenario, that's a -1 formal charge. It's got 2, 4, 6, 7, that's minus. This is minus. This is minus. This is minus. And then we look at the chlorine. The chlorine should have 7, but in this structure, it only got 1, 2, 3, 4, because it only gets half the bonding electron, so it gets 4. And so that makes the chlorine +3. Now that's a fairly high formal charge. You know, the oxidation state, of course, is +7, which is even higher, but this is considered a very high formal charge. And so sometimes we'll try to lower that formal charge by making multiple bonds, i.e. what we call expanded octets. Let's see what the book did. Okay, it's break time. The break, actually, they didn't expand the octet. They just left it. So this is relatively high. All right, so let's take a break right now, and then we'll come back after the break. And work on some more of these here. So this is the structure we ended up with here that I drew out, which is this structure here. In this structure, everybody has an octet. So chlorine has an octet, oxygens have an octet. But we ended up with kind of a high formal charge, +3. That formal charge means, like, you can think of it this way. Chlorine, how many electrons did chlorine contribute to the structure? Chlorine contributed 7. How many did it get out in the end? It only got 4 electrons at the end. And so it pooled in 7 electrons and only ended up with 4. That means it's 3 electrons short. So this is what gives it the +3. The oxygens end up with an extra 1. They put in 6 electrons in the pool, and then each of them got 7 electrons at the end. And so a +3 formal charge is kind of high. We try to minimize the formal charges if possible. It's not possible to lower the formal charge here if we have an octet. But this is something you might see, and that is if we form multiple bonds, we can lower the formal charge. So if we bring a lone pair and make that a bonding pair, then it's sharing that. This lone pair belongs entirely to the oxygen. Well, if this oxygen is willing, it can donate the lone pair to the bond. Now it's sharing it with chlorine. And so what that means is this oxygen is losing some electron density, so it's going from minus to 0. But the chlorine is gaining some electrons, and so it's going from +3 to +2. So if we expand the octet in this case, because now chlorine has more than an octet, oxygen still has an octet, so that's fine. But chlorine is going to have more than an octet. It's an expanded octet. And so if we do that again and make 2 double bonds, we'll go from +2 to plus, and these 2 oxygens will go to 0. If we do it a third time, then all these oxygens here are 0, except for this one over here, and the chlorine is now 0. It's got 1, 2, 3, 4, 5, 6, 7, like chlorine. So this would be quite an expanded octet, because count the electrons around a chlorine, 2, 4, 6, 8, 10, 12, 14. That's a hugely expanded octet. It's hard to expand it by that much. And so usually what you'll see for drawings, if you're going to expand the octet, maybe 2 double bonds is okay here. And so most of the structures I see are like this, with 2 double bonds. And so the 2 potential structures would be this. One with the octet, the high formal charges, and one with minimized formal charges. This one, it's because of 3 double bonds. Might be tough. This one, well, we could go 2 double bonds here. And so it will have. Now, if we have a structure like this is one resonance form. And so there are other resonance forms for this. How many? And so it depends on the positions of the double bonds. And so if we do this, another resonance form is, I could have made the double bond, top and bottom. That's another resonance form. Another resonance form is I could have made it bottom and left. Another resonance form I could do is left and right. And so these are the resonance forms that are possible for this particular structure. Here. Now, the true structure is all the bonds are the same. The bonds don't resonate from one form to the other. All the bonds are the same. And so we end up with something called the hybrid structure. Hybrid structure. Hybrid is a hybrid of all the resonance forms combined into one. And so if we go to the Wikipedia, let's take a look. Some of the other images for this, clear the drawings. We'll see different things here. This is with 3 double bonds here, 3 double bonds here. With 3 double bonds, we can have resonance forms here. This is shown in this drawing here. How many different ways of arranging 3 double bonds? Well, we could have left, right, bottom, left, right, top, left, top, bottom, right, top, bottom. So we have 4 resonance forms here. Let's see if we have others. Looks like most people are doing it with 3 double bonds to minimize the formal charge completely. All right, the true structure is going to be kind of a hybrid of these. And so this will be the hybrid structure. This is tetrahedral, by the way. So it's not flat like this. So it's shown tetrahedral like this. I would have drawn the tetrahedral a little bit different. You know, if I'm going to draw the hybrid structure of this, I've drawn the tetrahedral maybe like this. Sorry. 2 in the plane, 1 sticking out, 1 sticking in. And then just dotting the double bond is kind of, the double bonds are kind of dispersed throughout here. So that's what we get there. This particular ion perchlorate. Okay, they didn't do that. They just kept the high formal charges here. There are arguments to be made. There are arguments to be made for no double bonds, 2 double bonds, and 3 double bonds. All right, now let's take a look at these. These, now, what do we do here? These you have to know a little bit about the bonding, you know. For example, carbon has 4 valence electrons, so it likes to form 4 bonds. It likes to form 4 bonds. Now, those could be 4 singles. Or it could be 1 double and 2 singles. Or it could be 2 doubles. Or it could be a triple and a single. Just some kind of combination that'll add up to 4. Hydrogen likes to only form 1 bond. Hydrogen and fluorine, only 1 bond. Chlorine likes to form 1, but can form more. 1 bond, but can form more. Whereas these can never form more. Only 1 bond can never form more than 1 bond. That's what we get. So there are different ways of doing structures like this, you know. Structures like this, we could do our standard way, or we could just throw carbon in the center, and then we have a hydrogen. Well, hydrogen only forms 1 bond, and fluorine only forms 1 bond. So we'll bond those to carbon here. Now chlorine might, but chlorine prefers to form 1 bond. That works if carbon has 4 single bonds like this, then that works. And then this carbon will be tetrahedral, you know, it's got 4 single bonds. So we can arrange those 4 single bonds, 2 in the plane, 1 wedged out, 1 going in. Now, where we position these matters sometimes, but I'll just throw the hydrogen up top and maybe chlorine here. Throw in the lone pairs. I'm not going to do the lone pairs here 3-dimensionally. I'm just going to draw them flat. Maybe another chlorine here. And then a fluorine out here. And so the EPG, is tetrahedral. The Mg is tetrahedral. Now for ions, we don't talk about polarity because those are monopoles, but for molecules, we do talk about polarity. And so the chlorines are going to be pulling down and the fluorines are going to be pulling down. And so the molecular dipole is this end of the molecule looks red, and the hydrogen end of the molecule looks blue. Fluorine is going to be the most red because it's more electronegative. But basically, a dipole is just a red region and a blue region, you know, a negative region and a positive region. And so here, when we do in certain molecules like this, it might be simpler just to put these together like puzzle pieces rather than following the rules that are written earlier. Same thing with CHF3. H and F can only form single bonds. They can never be bridging. They always have to be terminal. And so what I'm going to do is just draw this. I already know it's going to be tetrahedral because I got 4 single bonds like this. Throw the lone pairs around fluorine. And so EPG, I forgot to write the angles on the last one. It's tetrahedral. Mg is tetrahedral. The angles here are going to be about 109 degrees. You know, maybe some slight distortions because of the size of the atoms, but they're all single bonds, so essentially the same. Now CCl3, well, actually, let's do it like this. The halogens like to form one bond if possible. Okay, so all these are single bonds. So the angle is going to be about 109.5. The EPG is the same. You know, EPG is going to be tetrahedral. Mg is going to be tetrahedral as well. The angle should be about 109.5. This is going to be polar, although this one's a bit tricky because chlorine's more electronegative than iodine. And so this chlorine should be the blue and then the iodine should be slightly red. I mean, excuse me, chlorine's more electronegative. So this is going to be red. These are going to be slightly blue. Here. Slightly red, slightly blue. So polar. This next series of questions get into something called isomers. You know, isotopes are atoms of the same element, different number of neutrons. Isomers are the same formula, different structure. So 2 or more acceptable diagrams, we call these isomers. Isomers. So C2H2Cl4. So there are 2 ways we could do this. You know, we could just, you know, have the Lewis symbols and put them together like puzzle pieces, right? That's one way we could do it. Another way we could do it is by our standard method, you know, 2 carbons, 4 times 2 is 8 electrons, 2 hydrogens, 2 electrons, 4 chlorines, 4 times 7, 28. So it gives us 38 electrons. Now, what do we do? Well, we put the least electronegative in the center, but we have 2 of them, carbons. So maybe we can put 2 carbons together. Carbons like to bond to one another. There's no problem with that. Oxygens don't. Oxygen does not like to bond like this. With a double bond, it's okay, but carbon-carbon single bonds is not a problem. So we'll put both of those in the center like that. Then we'll have 4 hydrogens and 2 bromines. And so each carbon likes to form 4 hydrogens and 2 bromines. Okay. Oops, chlorines. Not bromines, chlorines. Chlorine. So that's one possible structure like that. That would be one isomer. Another isomer might be, you know, rather than two bromines on one atom, we might put one bromine on each. Throw the hydrogens like that. This would be another possible. Or we put two bromines on the left, but two bromines on the left one would be the same structure as this if we just flip it 180. So that would be it. These are polar here because of the bromine. The bromine is going to pull electron cloud density. Polar. Now the structure for this is both of these carbons are tetrahedral. So let's do this one. I'm going to do the more symmetric one here. But we could do both of them. We wanted probably want to. So on this one, I got a carbon. Now this is going to be tetrahedral, 4 single bonds. So let's write in 4 tetrahedral single bonds like this. And so I'll have this bottom one go to the carbon here. And I'll have this top one, maybe I'll have it go to the hydrogen. This back one go to the hydrogen, and this front one go to bromine. Like that. Okay, then let's take a look at this next carbon here. So what I'm going to have is I'm going to have 2 in the plane. So I'll make a zigzag like that in the plane. And that means one sticks out like this, and then one sticks in like that. And so I need to throw another bromine on there. I could put it in any of these 3 positions. Yeah, I'll just throw it here. And then the hydrogen's up here. Yeah. All right, so what it boils down to is this. And then there's something called conformations. Conformations, single bonds can twist like this. And so what you see are these 2 bromines are next to each other. And the bromines are kind of big atoms, say. They're in the 3rd shell, 4th shell, something like that. And do you see they're kind of overlapping here? They're kind of close to each other. So what can happen is this can twist like this to get a more desirable conformation. So the more desirable conformation might be the bromines on the opposite end. So what I can do is I'm going to twist this around like this. Put the bromine maybe up at the top, maybe that might work, or off to the side. And so we can do that. That's conformation. Here, I can show you. But we aren't going to worry about it, conformation. You know, what we can do is we can let Spartan twist this and see where is it the best, you know, where is it the lowest energy, you know, as far as how I drew it. So let me just do that really quick here. I'm going to go organic. And then more. And then we'll throw in 2 bromines on there. See, right now they aren't too conflicted here, but they are kind of close. Another. So let's see what the best. Well, the best is if they're on the opposite ends. Do you see that? How it got twisted around? What we do is we can rotate this. I'll show you how to rotate this. Try to rotate it here. You see, if I twist it like this, you know, maybe they aren't as happy. This is called conformation. So right now, I drew it like this. The two bromines are right next to each other. Maybe that's not the happiest conformation, right there. But when I let Spartan do the calculations, Spartan puts them on the opposite ends. So let me go ahead and I'm going to replace that here. Now you can see they're on the opposite ends here. Like that. These are the types of things you worry about in organic chemistry, you know. But for us, we aren't really going to worry about it. Here, this is tetrahedral. This is tetrahedral. And do the space filling model here. You can see it. The polarity of this is going to be kind of interesting, though. Let's take a look at the polarity of this. You know, is it polar or non-polar? Polarity, we can use the electrostatic potential map here. What polarity looks like. This is fairly non-polar. Here, it looks very symmetric. Do you see that? Yeah. Okay, let's take a look at some more here. Oh shoot, I did, sorry, I did bromine. I didn't do chlorine. Chlorine's more electronegative. The chlorine should have been even more red. That's all right. Yeah. So there are two ways to build this one. Let me build it the second way this time. The first way I'm building it is using a model kit, like, you know, Lewis symbols and that kind of stuff. It's the same way I'm building it in Spartan. Over here, the proper way we're supposed to build this is like this. You know, we're supposed to first, step one, sum up the valence electrons. So I have 2 carbons, each one has 4, so that's 8 electrons from 2 of them. 2 hydrogens, it's gonna be 2 electrons. 2 chlorines, and it's gonna be 14 electrons. And then 2 fluorines, it's going to be 14 electrons here. And so altogether I have 28, 30, 38 electrons. And then I want the center atoms to be least electronegative. I have 2 of them, 2 carbons, it looks like there. And so this looks like I just have a choice, you know, where do I put the rest of the atoms? Now, this is going to be tetrahedral. And so there are different ways that we can draw the tetrahedral. 2 in the plane at a 109 angle. That means there's 1 sticking out and then 1 sticking in here. Now I'm going to do a more favorable conformation over on this side. And so the second one in the plane, I'm going to put it opposite and down like that. So it kinks like this, 109. That means 1 wedge is going to come out like this and 1 wedge is going to go in like this. So that means these 2 are, this is what we call staggered conformation. What I drew on paper was the eclipsed conformation, but this is staggered here. Don't worry about staggered and eclipsed. Now I have to worry about where I put the hydrogens and the fluorines. Well, the hydrogen and fluorines, figure that out. Well, I guess it doesn't really matter. Here, I have 2 hydrogens. Let me put the 2 hydrogens. Maybe let's try to make it like that. And then I have 2 chlorines. 1, 2. And then I have 2 fluorines. 1, 2. So this is one possibility. Another possibility is maybe I have 1 hydrogen on this carbon and the other hydrogen on that carbon. And so I can draw lots of structures for this, you know, depending on where I put the atoms. There's a lot of variations. Then I have the lone pairs. So how many electrons have I used? Well, this is 8 times 3 is 24. Times 4 is 32, 34, 36. Did I? 38. That's 38 electrons. So we're good. That's good. And so that's what we have. Of course, you could generate a different structure depending on where you put the others. Now, this is 3 carbons. Carbon loves to bond to itself. You know, carbon-carbon bonds are no problem. And so with 3 carbons, I'd likely make a 3-carbon chain. When we make a 3-carbon chain, we could do it like tetrahedrally because these are all tetrahedral. So that's 1, 2, 3. In this case, it's going to be kind of eclipsed in the way. So we'll have a bond like that. And then one wedged out and one wedged in. One wedged out and one wedged in like that. Okay, the same thing here. This is 2 in the plane, so that means one's wedged out and one's wedged in. This is just a single line here, not a wedge. It's not supposed to be a wedge. And then we got 4 hydrogens. You know, try to distribute them evenly, or maybe not. You know, 3 bromines and 1 iodine. So let's throw the iodine up here, and then a hydrogen, 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 hydrogen. It's 4 hydrogens, 3 bromines. We'll throw all the bromines here. Let's see, did we use up all the electrons? So that's 2, 4. Oh, I didn't count the electrons. I just built this. But when it gets to more complex molecules, you have to do this. In ions, you have to use this. For others, you can build it up like puzzle pieces, like in Spartan, for example, here. You know, we have the puzzle pieces here, different species. And this is your typical organic toolkit. Now, with Spartan, it doesn't do the charged ones. These are just the typical neutral species. So carbon likes to form 4 bonds. Carbon likes to form 4 singles, a double on 2 singles, a triple on a single. Or it could have this resonance. This is delocalization, this here. Silicon, 4 bonds. You know, oxygen, 2 bonds, 2 singles, 1 double. But it could also form 3 bonds. You know, oxygen can form 3 bonds if it has a positive charge, like in hydronium. Or oxygen can form 1 bond, like in hydroxide. You know, when we look at hydroxide, there's only 1 bond. We've got a negative formal charge, you know, the oxygen does. And so this doesn't account for those other bonding arrangements. So it's not just organic, but we have the inorganic. The inorganic, we can have these other kind of bonding arrangements here. And so you have to be careful of that if you're going to use the kind of this model building type thing I'm talking about. Organic. The oxygen, different bonding possibilities for oxygen. So here we have some more. This is a 6-carbon chain here. And we have 14 hydrogens. So this one, you know, I don't know how that is. I mean, it could be a ring. There are different possibilities. Or it could be a straight line. If it's a straight line, we kind of zigzag it like this. So let's see if we have to make a multiple. 1, 2, 3, 4, 5, 6, 6. And then each carbon is going to want to form, you know, 4 singles. So we'll add some here. And the only thing we have is hydrogen. 1, 2, 3 hydrogens, this is tetrahedral. 4, 5 hydrogens, this is also a tetrahedral. 6, 7, 8, 9, 10, 11, 12, 13, 14. All right, and so this is called 1, 2, 3, 4, 5, 6. This is called hexane. Okay. And they're all tetrahedral carbons, 109.5 angles. It's tetrahedral EPG and tetrahedral MG. Each of those tetrahedral. Other possibilities here is it could be something like this. Let's make 5 carbon chain. And then we'll throw the 6 carbon like here on this wedge here. Then another. And so this is what we call a branched. This is a straight chain. This is a branch chain. So we have that. You can throw an oxygen in there. Now, where is this oxygen going? Well, there's some clues. When you have an organic compound like this here, the way it's written can give you clues. So for example, if the hydrogen were in the front, let's say we have 1 hydrogen in the front. So let's say it's HC4H6O, then this hydrogen would be acidic. These hydrogens here, this should be 5, sorry to keep it balanced, should be non-acidic. So whenever we have an acidic hydrogen, this hydrogen's got to be bonded to oxygen, the most electronegative element here. Let me see what we're going to do here. So that tells us that, yeah, that hydrogen should be bonded to the oxygen. The other option that we often see is if C4H5OH, this tells me it's an alcohol. Here. Bonded like an alcohol. Or etc. So sometimes there's little clues. Sometimes there's no clues. In this case, there's no real clues because we can't assume, that's not an alcohol or that's not something else. But we can try different structures. So when we're given organic structures like this, we can build these using the kind of the model kit idea. Yes, we know, like, we'll just try to put everything together. So we got 4 carbons, and carbons like to form chains like this. And then we got 6 hydrogens. 1, 2, 3, 4, 5, 6. But now we have a problem here. So what do we do to this oxygen? Well, the oxygen, maybe we'll throw it out here and see if we can work that. Now, looking at the Lewis dots, we end up with something like this. So, this is not working quite right because we aren't getting the octet. And so we tried different things to see if we can get it to work. One of the things is we might take an electron here and an electron here and try to make a multiple bond. There's still going to be a problem over here. And so we could try a different skeleton in that case. Which one was I doing? I was doing C4H6O. I was doing this one. I think I missed this one here. And so we'll try a different skeleton because this one's not really panning out the way I thought. And so there are different skeletons that we could try. Like for example, C, C, and then O could be in the middle because O can be a bridger. like this. So even though it's the most electronegative, there is potential to stick it right in the center. But that means I only have 3 hydrogens for each side. And there's going to be a problem with this and this. And so we try different things and then see what might work. And so let me try another thing which might work, would be a CC. I'm not doing the structure whole thing right now, but let's go with an O like this, and then an H. C4H6O. So we'll try different things and then see how those work. But I think maybe we may let's take a break now. And let's take a break right now, even though it might not quite be break time, but we're getting close to the end. So we'll go for a break and then see what we can get with this right after the break. I'm thinking about how to put something like this together. So these skeletons aren't quite working out here. So we can try different variations. One of the variations is not getting enough bonds. So we could try rings is one option, you know, ring structure, or I could try throwing in double bonds in there. And so ring structure might be like this. And so we got 4 carbons. And so this would be a 5-membered ring here. And then I can throw in some double bonds in there. Maybe I'll throw in a double bond here and a double bond here. And then 2 lone pair here. And then check this out here. Okay, this isn't going to work because I'm only going to have 4 hydrogens. I need 6 hydrogens to complete everything. So maybe not a ring, maybe something like this. If I have something like this, except I get rid of the CH3s here, and then maybe I go double bond here, like this. Okay, now, if there is no formal charge, you know, each carbon will want to form 4 bonds. So this is double bond counts as 2, and then 2 singles here. This is 3, so I need 1 more. So I'll throw a hydrogen here. This is 3, I need 1 more. So I'll throw a hydrogen here. And then lone pair here. Now this works out because, you know, there's no charge here, so everybody contributes its valence. When everybody contributes its valence, it gets its normal bonds. You know, carbon gets 4 bonds because it has 4 valence electrons. Carbon gets 4 bonds, hydrogen has 1 valence, so it gets 1 bond. Oxygen has 6 valence. So 6 valence is going to need 2 bonds, you know, because it has 2 pairs like this. And so this structure works here. You know. This is a more complex structure. We could see, but there are isomers for this. You know, there are possibilities of other structures. But rather than spending a lot of time, like I wasted a lot of time thinking about this, one thing is just to see a lot of variations in the structures here. And so here they just did it. This is hexane, just a long chain, but it could have been branched. They did it differently. You know, they put 2 double bonds here and then they made an alcohol. I made what's called an ether here. And so, you know, both of these structures are fine. They have an octet and 0 formal charges. The same thing here. They put both fluorines on the carbon. Well, I could have put 1 fluorine here and then 1 fluorine here and then a hydrogen, hydrogen. That would have been another isomer. So these structures are complex in the sense that there are a lot of variations that we can do for it. And so let's move on here with this. Let's do butanoic acid. Butanoic acid, this is a structural formula, so this gives us a lot more clues. Like, for example, this hydrogen is bonded to the oxygen. These hydrogens need not be bonded to the oxygens. Then we've got 3 carbons. When we have these organic compounds, it's either 3 carbon chain, a 3 carbon ring, or something like that. 3 carbon rings, however, are unstable. You know, five membered rings, 6 membered rings, those are stable. 4-membered ring, 3-membered rings are starting to become unstable. So we have 3 carbons here. We can draw it in a line here. We don't have to go 3-dimensional just yet. Now this COOH group is a carboxylic acid group. And so it goes C with a terminal oxygen here, and then an O that's a bridging oxygen here, and then an H here. And then let's fill in the rest with hydrogens and see if it works. If it doesn't work, then we'll have to erase it and tweak it here. And so this is C3. Oh, sorry. This is C3, and then there's another C. So I'm missing 1 carbon here. I only have 2. And then COOH. So we'll go 3. And throw on hydrogens here. So this works. This is butanoic acid. Now to do this 3-dimensionally here, this carbon is going to be tetrahedral. It's tetrahedral EPG and a tetrahedral MG. The bond angle should be 109.5. So to do tetrahedral, we'll do 2 in the plane, 1 sticking out, this, and 1 sticking in. Okay, that's going to go to this carbon. This carbon is also tetrahedral. And so we'll do 2 in the plane. I'm going to do it zigzag like that in the plane, and then I'll have 1 sticking out like this, and 1 sticking in like this. This carbon is also tetrahedral, that. And so I'm going to draw 2 in the plane like that, and then 1 sticking out, and then 1 sticking in. And so this zigzag is what we expect when we have a carbon chain like this. It's not a straight line like I drew it here. It's a zigzag line like this. Now this carbon is not tetrahedral. This carbon has 3 groups. It has a double bond group, which it can't split into 2 groups. So double bond group and 2 single bond groups. So when we have 3 groups, that's known as trigonal planar. And so 1 group I'll put down here, like this, in terminal oxygen, and then 1 group in the plane. So all 3 of these groups are on the same plane. So this is 3 groups, trigonal planar. Now that's the EPG. The MG is the same because the bonded atoms are in the same configuration. So this is totally flat as a plane. Now this oxygen here, the bridging oxygen, has 4 groups. It's tetrahedral. And so if it's tetrahedral, what I'm going to do is I'm going to put the bonded atoms in the plane. And so I'll put the carbon and the hydrogen in the plane. So 2 single bonds in the plane. That means 1 lone pair sticks out and 1 lone pair sticks in to the plane. And so the lone pairs are projecting out and projecting in this particular case. And this has a tetrahedral, you know, the EPG here is tetrahedral, electron pair geometry is tetrahedral. However, the molecular geometry is different. The molecular geometry is bent, and this is bent at 109.5, but we expect it to be distorted by 2 lone pairs. If we have 2 lone pairs, 2-degree distortion per lone pair, and so it should be about 105 degrees distorted versus 109.5 degrees here. That's bent. This carbon here was trigonal planar on both. Trigonal planar on both the EPG and MG. And these were all tetrahedral at 109.5. Trigonal planar is 120 degrees. The double bonds take up a little bit more space here than single bonds. And so double bonds are like lone pairs in terms of taking up space. So it's about a 2-degree distortion. So this is ideal is 120. But what we expect for this particular angle is it's going to be widened a little bit. And so this angle gets stretched out a little bit. You know, the ideal is 120, but this one's going to get to about 122 degrees because of the double bond. This one's going to get out to about 122 degrees, and this one's going to be compressed. This has to add up to 360, so this one gets compressed to 116 degrees. We expect for the distortions. These ones, we don't expect any distortions. These all should be tetrahedral at 109.5. Both tetrahedral EPG and tetrahedral MG. And the angles should be 109.5 degrees. And MG tetrahedral. So that would be more the 3D structure for that. Here, the Lewis structure need not, Lewis structure doesn't have to show the correct angles or the correct shape, The Vesper structure needs to show it, and so this is the Vesper structure, more the three-dimensional type structure for butanoic acid, and we have the zigzag conformation like that. We can see butanoic acid. This is so this is the COO group here, and the H goes on the end here, so there'll be an H here. And it's a 4-carbon chain altogether, butanoic acid. So I'm going to have 1 carbon here, 2 carbons, 3. So total of 4 is but, it's 4. And I look at how it's shaped, the conformation and everything like that. Let's see how it's shaped. But, this is just how I built it. But it's not the lowest energy conformation. Lowest energy conformation looks like this. Oddly enough, this is the lowest energy. That's strange. I didn't draw it like that. I didn't draw it like this. I drew it, because I wanted to make it as easy as possible to draw. And so when I drew it to draw as many atoms in the plane of the page as possible. So when I drew it, this hydrogen's in the plane, this carbon, and so I drew it zigzag in a plane like that. But, to draw this three-dimensionally on a piece of paper would be kind of difficult here. And so what I did was I twisted it. And so, like, for example, I had the hydrogen up there. And so let me rotate this bond here. So I put the hydrogen up there. And then I twisted it to form a kind of this zigzag pattern to make it easier to draw this. Okay, this one I have twisted the opposite way. Let me twist this like that. And then let's twist this whole thing out. Okay, this is how I drew it here. The hydrogens aren't shown, the hydrogens, I put the hydrogen over there. So I get this one's the one that's pointed straight up here, this hydrogen. So this hydrogen's in the plane. This hydrogen sticks out. This hydrogen sticks in. This hydrogen's sticking out. This hydrogen's sticking in. And then it's going down to this carbon. So it goes down to this carbon. This carbon up here is in the plane. So this zigzag is in the plane of the page. That means this hydrogen sticks out. This hydrogen sticks in. Then it goes up to this carbon here. This carbon, then it goes down to another carbon. So this zigzag is in the plane. It's not completely in the plane. It's slightly rotated. But I just have to play with, let's see, I have to play with this one a little bit. Or no, I have to play with this one. Get it right. Okay, so I go up to this carbon here, and then this hydrogen comes out of the plane here, like I drew it up here, and this hydrogen goes in. Let me rotate this so I can get to that hydrogen there. And so that hydrogen goes in, so that's the dash there. And then we drop down to this carbon. This carbon's trigonal planar, so this is flat in a triangular plane. And then we have the terminal oxygen here that's double bonded. And then we have this oxygen, which is bridging to this hydrogen here. Well, it turns out this is going to be a conformational problem. If I throw the hydrogen here, then there's some interference there. So probably it's best to rotate this one. I probably should have rotated it down to make it one more zag. So look at zig, zag, zig, zag, zig, zag. So rather than going up, well, which I did, I probably should have dropped it down instead, like that, and drawn it. And if that's the case, there's one lone pair. We don't see the lone pairs. You don't pinpoint the lone pairs. One lone pair would stick out like this, and so I would have that bold, you know, and then one lone pair would stick in like this one in the back here, and that's how we would draw this. And so let's get some, maybe we'll get some more practice drawing these here. And so I'm going to just draw this on paper one more time here. And so starting off, oops. Starting off with a carbon in the back, I have it going to a hydrogen up there. Well, it's straight up there, let's say, pretty much, and then dropping down. This angle is 109.5. In fact, all the angles are 109.5. That's going to stick this hydrogen out like this, and this hydrogen in like that. And so this hydrogen is in the plane. This carbon's in the plane. This carbon's in the plane. And then we're going to bond it to a carbon. This carbon's going to be in the plane here. This is going to stick out. This is going to stick in. Yes. And then we'll throw in the next carbon. So all this zigzagging is in the plane. And that's going to throw this hydrogen out, and this hydrogen in. And then we're down at this carbon here, where we're going to have a terminal oxygen, double bonded, and then this oxygen. So the only difference is now I'm zagging this one down. So this hydrogen's in the plane. That's going to throw a lone pair coming out. Lone pair coming out, I make solid, and one lone pair going in. So this would be the wedged lone pair like this. This would be the dashed lone pair like that. And so this would be the way I draw benzoic acid here. Acetic acid is similar. It's a little smaller, so less to deal with. Now, NO2 plus, I wouldn't draw like this, you know, where I know the valences, and I know as long as I have zero formal charges, we're okay. But now I have a charged species. This is called the nitrosyl cation. And there I'm going to go back on the fallback rules, you know. That is, I'm going to use, well, we sum up the number of electrons. Nitrogen contributes 5 electrons. We have 2 oxygens, that should be 12 electrons, 6 electrons each. And then we have a +1 charge. +1 means -1 electron. So we got 17 - 1 is 16 electrons altogether. Now here, we want the least electronegative in the center. So that would be nitrogen. Nitrogen should go in the center. We'll put that. And then we'll bond it to 2 oxygens like this with single bonds. That takes care of 2, 4. But we have 16, so let's complete the octets to the terminal atoms. Okay, when we complete the octets to the terminal atoms, then we've used up all 16. So that's 8 on this side, 8 on this side, that's 16. But if you look at nitrogen, nitrogen doesn't have an octet. The total number of electrons surrounding nitrogen is 4. It's only 4. But I ran out of electrons, so there are no more electrons to put on nitrogen. And so what we have to do is we have to form multiple bonds. In this case, we're forming multiple bonds not to decrease the formal charge, like in perchlorate. We're forming multiple bonds so we can get an octet. And getting an octet is very important. And so what we're going to do is we're going to take one lone pair, which belongs entirely to this oxygen. So this oxygen is going to share this pair of electrons with nitrogen. And so we'll do that here. We'll make a double bond here, like that, by taking one of the lone pairs here. Now do we have an octet? Well, we still don't have an octet. And so we have to make another bond. So we can make a triple and a single, but that means this oxygen has to donate all the density. Well, that's not fair. So we'll make this oxygen donate one lone pair. And so we'll try to form one more multiple bond here. And so we'll get 2 double bonds like this. Okay, now it has an octet. And so this oxygen has an octet, the nitrogen has an octet, this oxygen has an octet. And so the octet is the most important. Then we look at the formal charge. This oxygen has a 0 formal charge. This nitrogen actually ends up with 1, 2, 3, 4. So it ends up short 1 electron, so it's positive. This oxygen is 0. So the nitrogen ends up as positive, and we have a net positive cation here. And that would be N. Now the structure of this should be linear. There are no lone pairs, and we have 2 double bonds like this. And so this should be linear. It's going to be linear on both EPG and MG. And MG. EPG and MG, linear. And the angle should be 180 degrees. That's what it should be. All right, so that's the nitrosyl cation. Let's look at dinitrogen monoxide or nitrous oxide. So nitrous oxide, we have 2 options. There's no charges on here, so we could try to do a valence and make sure everything has a 0 formal charge at the end, which may or may not be possible. With nitrogen, it's probably best just to go ahead and do it the formal way. For organics, it's like the organics that we saw up over here. It's probably easier just to build it using Lewis symbols and the correct number of electrons. And so here, let's take a look at nitrous oxide. We have 2 nitrogens, 2 times 5 is 10 electrons. Then we have 1 oxygen, there's 6 electrons. So altogether we have 16 electrons. Now for nitrous oxide, it looks as if the oxygen should go in the center. Because oxygen, bridging oxygen is no problem. Or we put nitrogen in the center. Usually we want the least electronegative, and so nitrogen's less electronegative, but oxygen sits in the center of water and lots of other things. And so there are arguments for both. Arguments for making it NON, which is more symmetric, versus NNO. Let's try NON first. If we try NON, we follow the rules. The rules are we complete the octets to the terminal atoms first. And so that gives us 16 electrons, but again, we don't get an octet around oxygen. So we could do the same thing we did with NO2+. Well, we're going to make 2 double bonds. 1 double bond on the left and 1 double bond on the right. And so that's going to drop the lone pair count to 2 lone pairs now here and 2 lone pairs here. And so now everybody has an octet. Okay, then we look at the formal charge. When we look at the formal charge, oxygen ends up with 1, 2, 3, 4. It's supposed to have 6, so oxygen ends up at +2. And this nitrogen ends up with 1, 2, 3, 4, 5, 6. It's supposed to have 5, so each nitrogen ends up at minus. This whole thing is +2 minus 2 is 0. Okay, let's try this one over here. When we try this one over here, let's complete the octets to the terminal atoms. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. When we do that, we end up with the same thing. This nitrogen doesn't have an octet. Now we have 2 choices here. We can have nitrogen sacrifice 1 lone pair, and we can have oxygen sacrifice 1 lone pair. So we'll take this lone pair here and this lone pair here. And so we end up with a structure like this. Now let's take a look at the formal charge here. 1, 2, 3, 4, 5, 6. This nitrogen ends up negative. 1, 2, 3, 4. This nitrogen ends up positive, and this oxygen ends up with 1, 2, 3, 4, 5, 6 is 0. Okay. And so this is fair. Nitrogen donates a lone pair, oxygen donates a lone pair. But let's say oxygen doesn't want to donate a lone pair. Let's say both lone pairs are going to come from nitrogen, which is possible. And so what we're going to do is we're going to donate 2 lone pairs and make a triple bond like that. Well, leaves only 1 lone pair left on nitrogen, and then oxygen is going to stay as a single bond. So if oxygen stays as a single bond like this, then let's look at the oxidation, or not oxidation, formal charge. 1, 2, 3, 4, 5. This is 0 here. This oxygen was 0 here. Nitrogen's 1, 2, 3, 4. This nitrogen is plus, and this oxygen is minus. So when we look at this, this structure has what we call high formal charge. If we can avoid high formal charge, it's better. Try to avoid. Now, these two structures have the same magnitude of formal charge, you know. This one has a negative charge on the nitrogen. This one has a negative charge on the oxygen. Which one do you think is better? A negative charge on nitrogen or a negative charge on oxygen? The negative charge on oxygen is better. And the reason it's better is because oxygen is more electronegative than nitrogen. In other words, oxygen wants the electron more. So oxygen is more electronegative than nitrogen. And so it turns out that this is the best structure. And so when we look for nitrous oxide, it's nitrogen sitting in the center, and it's going to be a nitrogen triple bond to a nitrogen single bond to the oxygen versus these other two scenarios here that we see. And so this is a tough problem. Let's take a look at nitrous oxide real quick here. N2O. And we see nitrogen-nitrogen triple bond, single bond to oxygen. Center nitrogen has a positive formal charge. The oxygen gets a negative charge here. And so that's what ends up being nitrous oxide here. Now, nitrous oxide is going to be linear because it has two groups, triple bond and a single bond group. So it's linear, and the bond angle is 180 here. All right, unfortunately, I'm out of time here, so I got behind again, unfortunately. But we'll continue. Tomorrow we're going to do lab, but are there any questions? We leave? When is the exam due? Monday. Exam is due Monday. It's the same as last time. Okay, sure. Okay, so I'll stop here. We didn't have a quiz today. There was no quiz today. I didn't quite make it far enough for you guys to do something yet. But tomorrow will just be lab. So I'll see you guys tomorrow morning. Thanks.